don't have evidence that it has active volcanoes or anything like that right now. What's the big difference between Mercury and Venus, between Mercury and the Moon and Venus and Earth? So the geologically active ones versus geologically dead ones. What's the fundamental property of the planet that makes them one or the other? The size, right? The size. Bigger planets stay geologically active longer than smaller planets do. So what the source of energy for geological activity is the planet's internal heat. A planet that's hot on the inside is going to be geologically active because, molten lava, right, comes out of a volcano. It's toasty. A planet that had cooled down on the inside is not going to be spewing molten lava, right? So geological activity comes from the planet's internal heat. Bigger planets hold their heat longer than smaller planets do for the reasons that we talked about on Monday.
So Jovian planets will
on Wednesday.
So Jovian planets will take a lot longer to become geologically inactive then?
Yeah, so in fact, they're kind of in a different category, and we haven't studied them in detail yet, but Jovian planets don't have geology because they don't have solid surfaces. So they're a different kind of planet. It simply doesn't apply. On the other hand, they do have a tremendous amount of internal heat still. That much is true. Like Jupiter emits 3 times as much energy as it receives from the sun. Saturn also emits more energy than it receives from the sun. Because in the case of Jupiter, it's still contracting. And in the case of Saturn, as you'll learn, the helium in it, Saturn is cooled more than Jupiter has, enough so that droplets of liquid helium are raining down towards the center. It's differentiating still, and friction on those droplets is heating the interior of Saturn.
So do metal and rock in the core have nothing to do with it being geological?
Right, yeah. The geological activity is all, there's a common misconception that lava from volcanoes comes from the Earth's core. No, it comes from the upper mantle. The core is way too far away from the surface to be contributing anything to the geological activity per se.
Cool. Thank you.
I'll get you, but yeah. Go ahead. No, you.
Me?
Your hand is up slightly first.
So, looking at Galileo's observations of Venus and Jupiter's moons, how did that support the heliocentric?
Yeah, it didn't prove the heliocentric theory, but it supported it. It made it. It made it reasonable, so to speak. So, and in particular, it did show. Well, let me find it here. Let's see. This is chapter 3, right?
Mm-hmm.
What is it? Just that it proved that they were orbiting Venus, so it wasn't possible. So heliocentric. Or no?
You're on the right track. So the phases of
heliocentric
Venus
wasn't possible because of that.
Yeah, right. So Venus's phases prove that it's going around the sun, which in and of itself doesn't prove Earth is too. But on the other hand, in Ptolemy's model, Venus was not going around the sun. Let me find this chapter 3.
I don't understand.
Was that because of the 2 new moon that we talked about with the epicycle and deference? Or is that something?
Let me just show it and then we'll play this. So, let's see, is this the right one?
I won't forget all of it.
Yeah, so here are photographs of Venus taken from Earth, and you can see it goes through a full range of phases, basically from full all the way to crescent does Venus. Now, in Ptolemy's model, Venus orbited the Earth, the Sun also orbited the Earth, and in Ptolemy's model, Venus orbited in between the Sun and Earth. Okay? So in Ptolemy's model, he had to have Venus stay near the sun in the sky, because it does. So in his model, the center of Venus's epicycle followed the sun around. But in Ptolemy's model, Venus was always in between us and the sun. Right? It looked like this. The reality is, Venus is sometimes on the far side of the sun from us and sometimes on the near side. So in particular, if we go to the correct description of what's going on, here's Venus at a new phase, because notice that the side of the sun the side of Venus that is lit by the sun is going to be the side turned towards the sun. When Venus is right here, it's its unlit half that is turned towards us, the side that is turned away from the sun. So in other words, Venus goes through new phase at which configuration, tying things back to something we were talking about earlier.
Inferior.
At inferior conjunction, Venus is at new phase. And Venus is at full phase when it is at superior conjunction, right? Because in that case, it's on the far side of the sun, and we're seeing the lit side of Venus. And then at these other places, it goes through the full range of all the other possible phases. It's gibbous here. This actually isn't quite right. It would be quarter when it was at greatest elongation. The quarter phases are at greatest elongation. This picture is a little wrong. It should really be more like right here to be at the quarter phase. And then it's crescent when it's in between the two elongations, closer on the near side of the sun, like this. In Ptolemy's model, notice Venus never gets to the far side of the sun. It's always closer to us than the sun is. So in Ptolemy's model, the lit side of Venus facing the sun is never fully turned towards us. So in Ptolemy's model, we would only see new or crescent phases because the lit side would always be facing the sun, which was further away from us than Venus was. And so, in other words, what Galileo had showed is that Venus must be orbiting the sun. That doesn't prove that Earth is orbiting the sun too, but it makes it plausible that if Venus is going around the sun, why not Earth too? You know, Earth could be just another planet too. And of course, now we know it is, and it wouldn't make sense in terms of gravity, no matter what the silly flat earthers say, it wouldn't make sense in terms of our understanding of gravity for Earth not to be going around the sun too. It's driving me nuts these days. Every time I look up videos to show you guys, there's these idiot videos on the side from these flat earthers, and I'm like, this is ridiculous. It's like, what is happening to this world? But anyway, so that's one of them. Another one is the Galilean moons of Jupiter. Okay, there was an argument that the old school folk, so to speak, had made that if the moon, if Earth is going around the sun, it should leave the moon behind. They argued, you know, why would the moon follow us around the sun? Well, it does. Why does the moon follow us around the sun? Why don't we just leave the moon behind? Gravity, because we're pulling on the moon with our gravity, right? Well, they didn't understand that back then. It hadn't been realized yet that the same thing that makes apples fall to the earth is what holds the moon in its orbit around the earth. That wasn't understood yet. Now we do understand that. What Galileo's observations of Jupiter's satellite showed was that Jupiter has moons going around it, and Jupiter, no matter what model you took, Jupiter was supposed to be moving, whether it's moving around Earth or moving around the sun, Jupiter was supposed to be moving, and it had moons, and it wasn't leaving them behind. So Galileo said, if Jupiter can move and not leave its moons behind, why couldn't Earth also move and not leave its moon behind? So again, he hadn't proved per se that Earth is going around the sun, but he had answered an objection of people who argued for the Earth not going around the sun. He said, well, no, Earth could move and not leave the moon behind because Jupiter moves and doesn't leave its moons behind. So there must be some way for that to happen. Yes?
Could you explain how tidal forces arise in the row? Yeah.
Right. So one thing I will say is tidal forces are complicated, and to be perfectly honest, I have never taken the time to really and truly understand how they work. So I can give you a good enough explanation.
Just give me a test-worthy answer.
I will give you a test-worthy answer.
Honestly,
okay. I know, and I knew that that's what you wanted. I'm just saying, I just kind of wanted to throw that out there, that
They
it
can-
turns out tidal forces are actually rather complicated to understand, even for physicists, in terms of the full details of how it works. But I can give you an explanation which will satisfy you, yes. So, which chapter is that again? Is that 4?
4. Yeah, I think it's
Okay. So, tidal forces arise because of the, but I don't think I put the slide on 4. That's silly of me. So where do I know where it is in the book, so I'm just going to Google tidal
I don't know
forces.
if we went over it in class.
No, we didn't, I know, but it's in chapter 4 is what you're saying, right? So,
Yeah.
Yeah.
right. Actually, what I can do is this. I have all of the figures from the book, and I will just pull it up. Yeah, that was one. There's only so much I can cover in class, and we actually are going to talk about them some more when we talk about some other things, but I just hadn't gotten to them yet. But I figured, well, that I have them read the book for a reason. So I have to find it here. Courses, and then textbook figures, and then our book, which is the 21st Century.
No, it's Bennett,
Cosmic
Cosmic.
Perspective.
Yeah, Cosmic Perspective, right, that's another one I used to pass, yeah. Hello.
Chapter
Yeah.
4.
I know, yeah. And then chapter 4, okay. And then images. And then, God, okay. And I did, no, this is good enough. They got this PowerPoint, just got every one of the images. And then I just have to go through the damn thing, so I should open it and read the slides. This is only a simple 56-step procedure. Open with Google Slides. Okay, here we go. Anyway, what it's fundamentally coming from is, so the moon, okay? The force of gravity that the moon exerts on something depends on how far away from the moon you are. And that means the following. Here's the Earth, here's the moon. It's not to scale. The moon is really much further away than this, but whatever. This side of the Earth, the side of the Earth that is facing the moon, feels more gravity from the moon than the side of the Earth that is on the far side away from the moon. So the moon is pulling harder on one side of the Earth than it is on the other side of the Earth. And how hard it's pulling on the center of the Earth is in between. And what it comes down to then is, as the figure here is saying, the difference in gravitational attraction tries to pull the Earth apart, and that's what produces the tidal bulges in the ocean. There's 2 tidal bulges. One of them is facing the moon, and the other is facing the opposite direction from the moon. So notice it's symmetric. Both tidal bulges have the same shape, and it's more complicated than this, and certainly it's not as this big. I mean, the tides only go up and down a few feet, and this is make it look like it's 1,000 miles or something like that. So this is exaggerated for clarity, but the difference in the force of the moon's gravity on the near side of the Earth from it and the far side of the Earth from it raises a pair of tidal bulges, one facing the moon, one facing away from the moon. It's symmetric. That's a little counterintuitive and a little hard to understand why that is, but it turns out they're symmetric like this. There's a bulge facing away from the moon and a bulge facing towards the moon. And the Earth is turning. And so if you live in a coastal area, then you are going to, when you're on the side that, as you are carried into the tidal bulge facing the moon, you have a high tide. And then over here you have a not neap, it's just high versus low in any given day. I'll get to neap and spring in a minute. So in any given 24-hour period, if you're near the oceans, right, where you can actually see this effect, there's tides on solid land too, but it's like a matter of like, like a centimeter or something like that, so you don't notice it. So you only notice it in like coastal areas for the most part. So this is high tide, and then about 6 hours later you get not a high tide, but a low tide. Another 6 hours later you get another high tide, and then another 6 hours later you get a low tide. So you have 2 high tides and 2 low tides every day, almost 12 hours apart from one high tide to the next, but not quite, because the moon is moving in its orbit, and so as a result it's a bit more than 6 hours to the next high tide, but they're about half a day apart. So every day you get 2 high tides and 2 low tides, and one of the high tides is when the moon is high in the sky, and the other high tide is when the moon is in the opposite, well below the horizon. The other piece of that is that the moon isn't the only story here. The sun also raises tides on the earth, because the sun pulls harder on one side of the earth than it does on the other, because one side of the earth is closer to the sun by a little bit, one side is further from the sun. And so the moon is primarily responsible for the tidal bulges, because the moon is closer to us, and even though the total force it puts on us is weaker than the sun's force, the difference in the force across the earth is bigger for the moon than it is for the sun. So the moon is primarily responsible for the earth's tides. So the tidal bulge always points towards and away from the moon, but the sun also contributes. So when the sun and the moon are in the same or opposite directions from one another, in other words, at new moon or at full moon, then the sun's tidal bulge is reinforcing the moon's tidal bulge, and you get the biggest possible high tides. And those are called spring tides. Because it's kind of like, because it's the water's springing up more, if you like. But when the sun and the moon are at right angles to one another, then they're working at cross purposes, and you get the lowest possible high tides, and those are called neap tides. So spring tides, when you get the highest high tides, happen at new moon and full moon, and neap tides, when you get the lowest high tides, right? Careful, right? I said the lowest high tides. Those happen at first quarter and third quarter, because there the sun and the moon are working at cross purposes, perpendicular to one another in terms of trying to raise tidal bulges, as opposed to working with one another to raise tidal bulges. Yes?
In spring tides, it also has the lowest low tides, right?
I think that, yeah, I think so, but really I think that's right. I would know more for sure if I lived in a coastal area. I don't pay attention to tides because they don't really affect my life, to be honest, but it's probably it ought to be the lowest low tides too. Yeah.
You know this.
I know this, what do I
Like
know?
I'm saying, like I'm like Massachusetts, like you notice when the tide is.
Oh, yeah. Right, are you from Massachusetts?
Yeah.
Yeah.
So it does make a difference, and there are different problems that it affects, like the whole like ecosystem and everything.
Yeah. When I was in China back in 2009, I went to a river where there's a famous tidal bore, where this wave goes up the river because of the shape of the estuary. It creates this wave that goes up the river, and it's really pretty cool. I have this nice video of it, which maybe I'll show in class at some point. But it wasn't on a day. Sometimes it gets really large, and people have been like swept away by it and stuff like that. Yeah, it's pretty amazing. So maybe I can show it in class. I should take time right now for that. But it's a true tidal wave. What people call tidal waves that people surf on, those are not actually tidal waves. Those are caused by like the wind blowing over the ocean, and then the waves come towards shore and steepen when it gets shallower near the shore. But the tidal bore is a true tidal wave. It's caused by the tides, and it's really cool. Anyway, that's just an aside. I want to double check that the camera is the camera still got a flashy red light on it?
Yes.
Yep, okay, good.
nebular theory.
Yeah, the nebular theory is the whole thing. The nebular theory is this whole idea of the sun formed from a cloud of
Right.
gas and dust, and as it shrank, it flattened out into, part of it flattened out into a disk, and
Yeah.
the sun and planets formed in
Right.
the disk. I mean, the sun formed in the center, and the planets formed in the disk.
Yeah, the only thing I'm confused on is like the exceptions to the
Mhm.
rules, if you could
Right.
go over those.
Right, so the exceptions, right, so we were supposed to explain all these things, right? So So why are all the planets orbiting the sun in a plane and almost in the same plane and in the same direction? What's the explanation?
Because in the nebular theory, that's how it was formed and that's how it started rotating, so the planets rotate in the same direction that.
So, right, so they rotate, they go around the sun in the same direction. The cloud was spinning, and they formed in a disk. And so they orbit the sun in the plane of that disk, right? And so you know, that's not an exception, right? That's what we expect. Computer simulations show that they should be rotating in the same direction that the disk was spinning too. That's not quite as obvious, but it turns out to be the case. So there's all those properties, and then there's but wait, there's exceptions to the rules. What are those caused by? What are most of the exceptions to the rules explained by? Remember? Like why do we have a big moon? We're the only terrestrial planet with a big moon.
The impact, the great impact.
Yeah, there was a big impact, right? A massive impact of something the size of Mars smacking into Earth, right? So we understand Earth's big moon in terms of a so-called giant impact. What's another exception?
The direction, like the rotation of Venus, right?
Yep, Venus is spinning backwards, and while we don't know this for a fact, what's a possible explanation for why Venus is spinning backwards?
Off-centered collision.
An off-center collision by a giant impact. Yes, a giant impact, it's possible that a large protoplanet smacked Venus off-center and started spinning slowly in the opposite direction that it originally was spinning in. What's another exception?
Tilt, right?
Tilt of Uranus's axis of rotation. How do we think that came about? There's a pattern here.
Being hit by something.
Being hit by an Earth-sized protoplanet. In other words, it was, we think, probably caused by a giant impact. Yes. Most of the exceptions are thought to be giant impacts. And again, you know, it's the exception that proves the rule, where proves really means tests it. So if there are exceptions that you can't explain, you lose confidence in your theory or you think you need to modify it. But in fact, we would expect there to be some giant impacts, because in the end stages of planet formation, there would have been a population of large protoplanets that is not at all surprising would sometimes have had collisions between two large protoplanets. And so having some of those would in fact give us the expectation that there would be some exceptions to the rules that could be explained by giant spectacular impacts like that. That's not the only, another exception to the rule is that Neptune has a moon called Triton that is going around it backwards, so to speak. We don't think that's caused by a giant impact. We think that Triton was a Kuiper belt object that got captured by Neptune. It might have been a binary Kuiper belt object. It had two Kuiper belt objects like similar to Pluto orbiting one another.